All right, welcome everyone. This is your final breakout of the day. Then there'll be one more session all back together as a group here in Tremont. Welcome to the Rethinking Fertility session. Does anybody have a guess of what this is going to be about? Give you a hint. Probably fertilizer, right? We're talking agricultural fertility here. My name is Corey Mulbauer. I'm the lead agronomist in our R&D department at Precision Planting. I've been in this role for 7 years now. I've been with the company for 10. My involvement with R&D, what my role is there, is to basically work alongside of our engineering teams developing products to help together decide in what ways do we need to measure the problems in the field that we think we can solve, as well as then bring our prototypes and those things out to the field and measure again whether we're making a difference as far as helping solve some of those problems. And a lot of the things that that we get onto as far as potential things in the field that we should be looking at, it comes from you guys. So I really appreciate all of you guys here in Tremont as well as at the simulcast locations for being a part of this event, because all of us Precision Planting employees probably have 50 conversations throughout the week with different farmers, and it's that sharing of information that is really valuable to us. So as we learn new things from you and also things that we think of ourselves, I set up trials and test plots and try to go out and learn and put value to some of those things. And sometimes it's pretty forward thinking as far as maybe it's not even related to a product yet, but I think it's important to understand what we could be doing different. And so fertilizer is a gigantic topic, and we started working in this space about 4 years ago. Looking at opportunities to increase the efficiency of fertilizer. It's a big expense on the farm, and we want to do a better job with that and see if we can move the ball on getting higher ROI with our fertilizer expense. So a little history on fertilizer. I kind of dug up some of the earliest time periods at which I could find when commercial application of fertilizer or just fertilizer usage on the farm in general was starting to be done. A little over 100 years ago, in the early 1900s, I found some records of fertilizer being applied to some farms. So you see here, the standard method at that time was broadcasting fertilizer. You got a couple of farmers there with a horse and wagon, and they're pitching the fertilizer out the back with a shovel. And as I think it's kind of neat in this picture, I think they're contouring right around the side hill there. And they may possibly even be doing variable rate. When I look at the distribution of the fertilizer, it doesn't look real uniform, and I don't know if that's intentional to optimize the fertilizer rates or if it's maybe poor performance of application. I'm not sure. So we've come a long ways in the last 100 plus years of fertilizer management. At least we believe we have. Still today, the most standard application of fertilizer that I see is we're still broadcasting fertilizer. And broadcasting is maybe not the most efficient method to be doing it. We have advanced significantly in the way that we measure what fertilizer we need, right? In the last 50 years or so, we've developed soil testing processes and laboratory data analysis so that we know what the level of fertility is in our soils, and then we can fine-tune how much fertilizer we apply. But I think it's a little bit of an issue, and there's opportunity that remains, the fact that the majority of our nutrients are broadcast on our fields. The concept for building and maintaining our nutrient levels in the soils comes from the idea that the soil is a bank for our fertilizer. And so as we broadcast P and K on our farms and we increase the value of P and K in the soil, that soil bank holds on to those nutrients, and then it releases it to the crop during the growing season. And as long as we maintain the bank full enough, our crops will be just fine. The reality is broadcasted P and K products, when applied to the soil, only about 10% or less of that fertilizer nutrient is actually available to the crop the same year. So the response to that immediate application is not a guarantee. It's a little bit inconsistent. A soil bank is unreliable on how much it releases on any hour of any one day during the growing season. That's because it heavily is dependent on microbial activity in the soil, which is dependent on weather patterns, rainfall patterns, temperatures, things like that. It's way different than the banks that we put our assets into, right? When we put cash in a bank, We have the ability to go to an ATM machine on any day and we can withdraw exactly what we need to get by. It covers our needs of that day, and we can do that as much as we want. In fact, it's so easy today, we can just pull our phone out of our pocket and we can make a payment or a withdrawal anytime we want. So our accessibility to the banks we know is much different than the soil bank that we're building up for our plants. It's much more unreliable. The reason why it's this way is because that soil bank is the CEC of the soil, cation exchange capacity. It's a measurement that's reported on your soil test report. That is driven by the organic matter primarily, and then secondly, the clay content of the soil. This combined adds up to the negative charge sites in the soil that hold on to all of our nutrients. Once the nutrients that we apply are bound to those negative sites, then we don't get to decide when they get released. Again, it's variable depending on weather patterns, seasonal differences, and things like that. In solution at any one time, there's less than 1% of the total nutrients that is in that soil bank actually in solution at any one time. And again, it's extremely variable. So there's probably better ways to do it. Another thing about the way that we're currently managing nutrients in our farms is again, I talked about we soil sample and we build our soils up to a certain level to create optimum yield potential. So this has been a big improvement over the last 30 years or so, looking at what's the optimum soil test level to achieve yield. But again, it's based on the inefficient method of broadcasting and building a soil bank, right? So this is an example here, this chart, from 15 to 90 part per million per acre on a phosphorus soil test across the bottom there. And university trials have categorized the very low, low, optimum, high, and very high ranges of these soil test values. You see those in text there. And the idea of building and maintaining soils is to apply enough broadcast fertilizer to get the soil test value to that optimum range. And this is the range that through years of trials, they realized there's no limitation to yield, and any additional fertilizer is not going to create more yield. And that's where we've parked it. But the data points on this chart, all those black dots, in 2016, Pioneer did a report on yield response to soil test values, and they have 22,000 soil samples in this data set, and they compared those soil samples to 50 feet of yield data near each one of the samples, and you can see the yield correlation to phosphorus soil test values. And so the first thing I see when I look at it is it looks like birdshot from a shotgun. I'm a pheasant hunter, and I have to use birdshot because I can't hit a pheasant flying through the air with a rifle. And this looks like birdshot hit the screen, and we got very poor correlation to yield when it comes to soil test values of phosphorus. What I see up here is all the way over there at 15 part per million phosphorus is when we actually start to see a decline in yield as we move to the left. Everything to the right of that point, you could say there really is no correlation to the soil test phosphorus levels, and why is that? It's basically because everything above that point, on average year after year, we're getting enough phosphorus in those plants. And I think the reason why, and this is my assumption, is the reason why the university ended up putting the optimum where it is because we have variability year after year of what the soil can release, right? It's very weather dependent based on how the soil holds nutrients and releases nutrients. And so year over year, they wanted to pick the category that's a guarantee that if we give that recommendation out to all the agronomists writing recs, that if you build soils to this level, there will never be a limitation to yield. But I believe with newer technology and newer management methods, we can live over by the 15 part per million range in our soils, and we could pull back on the amount of fertilizer we put in the soil bank. And how are we going to do that? We can do that by moving those pounds of fertilizer into banding methods and also doing better measurements and some of those things. So this is where I think we could be going. I think we could be shifting our mentality on how we actually manage our nutrients. And the end result could be less fertilizer purchased, higher yield potential, and some of those things. To get there, we're going to have to be banding more of our nutrients, especially our nitrogen and phosphorus. We're going to apply more in season to optimize the time at which the plants need those nutrients. We're going to soil test more often. How amazing is it when there's data available to make an accurate decision right before you spend money on an input? Okay, soil testing standard today is we go every 4 years. It means we guess 3 out of 4 at what our crop is going to need, plus how much the soil is going to give it, and we get 4 years down the road and we adjust because we're typically wrong by the time we get there, or we've overshot and over-applied. And then use smarter zones. I think smarter sampling methods are going to be a thing of the future as well, and how to further dial in these fertilizer programs. So moving on from that, we've got some trials where we're actually looking at what's the opportunity of economics and yield if we try some concepts with banding in our program to achieve a maximum efficiency per pound of fertilizer used versus the idea of just building the soil test levels up really high and maintaining yield that way. So we've got these fertilizer program plots up by Morton. The Ackerman family works with us to allow us to do a number of trials on their farm. So the 4 main programs that we're doing on this field, and we've got 2 years of data so far and hope to keep this going as long as we can. We're looking at nitrogen only blocks. So this is no phosphorus and potassium applied for that 2 years. Just to give you a foundation of this field, based on the agronomy handbook recommendations, this would be a low category for phosphorus and potassium levels in the field. 10 part per million phosphorus, 75 part per million potassium. So we're probably going to get some response from the fertilizer. But the second block then is providing the phosphorus potassium nutrients, but 100% of that in a band and only putting on the crop removal amount. So we've got a 220 bushel yield goal on this field, and so we're putting on that much phosphorus and potassium. The third block or treatment is the same banded removal rates, but also applying a small amount of broadcasted phosphorus and potassium, whatever we need to meet the minimum soil level that creates a good, healthy soil environment. So basically, if you think back to that chart, maintain the soil right at that 15, 20 part per million, so we've got full yield potential from the soil itself. And then all the way to the right, that last block is the agronomy handbook recommendation to build the soils on this farm up to the optimum levels in a 4-year period. And so that 240 and 200 pounds of potassium and phosphorus, that's actually 400 pounds of potash per year per acre, 400 pounds of DAP per year per acre to achieve those and fit that recommendation. So visually, as we do drone flights over the field, we scout the field, we can always pick out the blocks that have banded nutrients in them. The band providing that maximum efficiency and root availability really shows in growth and health of the plants and uniformity of the plants. We scout all season and we're collecting tissue and soil samples, which we'll share more in the future on these. But we're always seeing this visual difference. It's very significant as far as the applications of P and K in the band. And even all the way to tasseling. So as an agronomist, one of the best times to scout a field and evaluate how good we're doing in a field as far as consistency of plant development, you look at the tassels. And what the tassel represents is how uniform the growth and maturity is of every plant in that farm. And the goal is to have carbon copy tassels all the same height across the whole field. And you've done the optimum job of advancing the growth in that field without any limiting areas. And so on the left-hand side of the screen, you can see the banded block, and every tassel is a carbon copy at the same height. In the center of the screen, you see the nitrogen-only block where we didn't put any P and K on, and it's way behind in maturity. It's not even tasseling yet. And then on the far right, you see the 400 pounds DAP and potash broadcasted, and I still have inconsistent tassel development. So even though there's 400 pounds of DAP and potash, we still aren't adequately feeding every plant the same. And so what happened to that 400 pounds of DAP that would have kept the maturity on track? It's tied up in that soil bank, right? That bank is not efficiently feeding those plants consistently across the field. And so it's locked up in the soil bank and the CEC side of things, and we don't know when it delivers that back, okay? So it's a more unreliable way to deliver nutrients to the plant, and it shows in the variation in maturity there. So the cost of these programs, we of course have to evaluate the economics, right? Because that's everything in business has to have profit, and we got to understand what's the most profitable scenario. So for these 2 years, the cost of the programs in nitrogen only being only $85 an acre. So that's pretty attractive. If all we care about is spending less, we just put on nitrogen and we'll get by. And then all the way up to $234 an acre on the far right to do the full build the soil up as well as achieve yield. So the question is, will we pay for, will we make money on that additional $150 an acre across the range of these different programs? Yield-wise, this is our 2-year average yield. So nitrogen only is running around 165 in the last 2 years. And so there's a huge jump as soon as we start addressing the P and K needs of this crop. And I think this is a good point because nitrogen is always number one, and P and K doesn't get talked about that often, but those are actually very important nutrients. That's why they're part of the macronutrient list as far as their importance and value there. So there's 60 bushel advantage just by addressing the P and K needs of the crop there. But then you also notice that from right to left, the more P and K we're putting on, the higher the yield keeps going, right? Even all the way to that agronomy handbook program, it's the highest yielder so far in the 2-year average. But when we look at the economics, the bars shift a little bit. And so the nitrogen only, we're only making about $500 an acre after we pay for the fertilizer based on those yields. And then we're in the 650s in the middle two, and then we drop a little bit as far as the ROI on the fertilizer program. So the optimum program is the one where we're balancing both banded applications of the P and K plus a minimum level of soil build just to maintain some of that soil health there. I think the combination is best, and it kind of makes sense to me. The soil, especially through the Midwest, provides almost half the nutrients that our crops actually grow. The pounds that we apply in fertilizer is far less than the total it takes to grow the crop. So we have to have some consideration for the soil itself and the fact that the roots are tapped into 100% of the soil profile, and we want to utilize as much of that as possible. But I think the inefficiency is relying 100% on building soils up high and that soil bank feeding our crops. So there's $36 an acre additional profit gained in the banding program with minimal soil build as compared to the full soil build program in this example. It's also interesting to think about the efficiency of our money spent. And so what I did here was I took the dollars spent on the phosphorus programs versus the dollars gained in yield. And if you look all the way to the right, even that high soil build program, we're still getting a 3x return on our dollars spent. So there is no doubt that fertilizer programs are worth the money. If I can spend $1 on something and get 3 back, I'll invest in that all day long, every day. That would be phenomenal. And I think everybody would agree. But what this chart I think really tells us is when we're making decisions to cut back on fertilizer, we should also then, very next thing we think about after that is how do we get more out of the limited pounds of fertilizer we want to apply? And that's the banding methods in the center and to the left. There's a 5 and an 8x return on the same dollars spent when we start implementing some banding of those nutrients. So those are big opportunities as we start cutting costs in fertilizer to be shifting to banding methods instead of broadcasting. So it helps to understand each individual nutrient itself, where are we getting these responses from and that sort of thing. So we take phosphorus, for example. One of the primary times of the year that phosphorus is a challenge for the plant to adequately get a hold of is right at the beginning of the season. And the reason for that is the beginning of the season, we're typically cool, and we have to have soils above 60 to 65 degrees to get adequate phosphorus from that soil. And that's because the microbes are a major component in converting phosphorus tied up in the organic matter into phosphorus in solution for the roots. The root mass of a corn plant is also very small early in the year, and the limited available phosphorus is out of the plant's reach until the root system covers 100% of the soil profile. So we're limited in the reach of that plant to get phosphorus. And then also phosphorus is a completely immobile nutrient. It only moves about a millimeter in a season. The reason is that negative charge latched onto positive charge cations in the soil doesn't allow it to move, so the roots have to go find it, and that's not a real efficient process either. So the opportunity is to start banding some phosphorus early in the year, at the beginning of the season. The planter is a good pass for that, so starter fertilizer is one of the primary reasons why we got those different results in that plot. So we set out 4 years ago to figure out what's the best or most optimum starter fertilizer placement. And we learned that relative to the furrow or to the seed, the best place to place starter is right where the seedling roots begin to grow. So right by the seed in furrow always gives the best response to a starter fertilizer. And so you can see where that is on this graph here. And then also we wanted to learn what's the optimum rate of a phosphorus-based starter fertilizer. And our plots typically told us that somewhere around 8 to 10 gallon per acre of a polyphosphate is the optimum rate and return on investment. So we had a conflict, right? We can't put 10 gallon per acre of a polyphosphate in the furrow because then we're at a level where we could have some seedling root burn and some seedling burn, and that's a negative impact on that crop. So we had to create a multi-band applicator. So FurrowJet is what emerged from that. So a couple of years ago we came out with FurrowJet. Its triple band application allows you to get 1/3 of the product in the furrow safely, and then the other 2/3 are knifed into the sidewall, soil applied, to allow us to hit that optimum rate. So FurrowJet is what was used in the plots. We've also been studying just starter by itself as far as what value it creates in moving some of the broadcast pounds of phosphorus into the starter band on the planter. So 15, 16, 17, I got a whole bunch of pictures, 18 of somebody standing in the field with their arms kind of goofy like this, representing the difference in growth, height, and health of those plants when we band the starter versus just a broadcast program. And so here's a summary of the 4 years of multiple trials and our yield responses. And phosphorus being very weather dependent as far as its availability, we get different results year in, year out, and in different fields. So this is kind of everything together here. In 2015, we had a very cold, wet year, so some of our strongest responses came from our first year. 10 to 27 bushels per acre on average was the range. And then in 2016, we had one of the best seasons we've ever had. We got warm early, and we stayed warm all the way through early plant development. The soils were warm. We got adequate rainfalls that year. So our starter response was 0 to 5 bushels. You know, something to just kind of shrug your shoulders at there. It's not real impressive. And then 17, we had a wild range of environments depending on which county our plot was in. So that variability across the state of Illinois created 0 to 20 bushel responses in starter. 2018, we ranged from 3 to 18 bushels per acre in starter. So if we average all 4 years together, it's about a 10.3 bushel per acre average of banding some phosphorus with the planter versus broadcasting those same pounds of phosphorus. That averages out to be $30 an acre increase in profit in that fertilizer program. And I think that's pretty representative because you all know that variability season to season is a real thing, and you should never expect the same results every year. It's always going to be variable returns. So our fertilizer planter that we've been using in plots is the one in the picture there, and there's about 5 to 6 different ways on every row that we can apply fertilizer. You can even see there's a broadcast nozzle out the back. That's how we typically do our checks. That way every treatment has the same pounds of fertilizer across the plot. So we're just evaluating the broadcast version versus banding it near the row. It's a placement study. To achieve adequate rate performance and accuracy, we've got V-Apply HD modules on every row, and that makes it so that when we pull the hose off of the coulter that's 2x2 and we move it over to FurrowJet, there's different back pressure on that fluid, and the V-Apply HD module just makes sure we're always hitting the rate exactly what it needs to be for the plot. So we also want to understand how to evaluate the cost of starter. And this is something that in the industry has been missed quite a bit because a lot of people calculate the cost of starter as a full added cost to your bottom line. And that's not the way that an agronomist who does nutrient management plans would add fertilizer into your system. When you do a nutrient management plan, for example, this is for the phosphorus needs of a high yield corn crop. You see at the bottom there, total P2O5, 92 pounds. So we're going to need 92 pounds per acre to meet the grain removal needs of a high yield corn crop. To achieve that in a broadcast form, we'd put on 200 pounds of DAP, and that costs about $48 an acre. Okay, so then if you sit down with your agronomist, you say, I want to add starter on my planter. So we'll pick 8 gallon per acre of 1034O, and your agronomist says, okay, for your yield goal, we still need to hit that 90 pounds an acre of phosphorus, so we can reduce your DAP application to 130. The rest of the phosphorus comes from your 8 gallon of 1034O, and this total program now costs $54 instead of $48, or $52 instead of $48. So what's the actual additional cost to do the starter program versus the all broadcast program? It's about $4 an acre for this polyphosphate example of starter. So how many bushels do we need to make money on a starter program when you actually reallocate the nutrients to hit the same total for the year? Anybody want to give me a number? It's tough math. We're $3.50 average price of corn. About 2 bushels, right? And we're already making money. So this is the right way to evaluate the cost of starter and the ROI. Is it should always be integrated into your total program, and your nutrients or your fertilizer should be reallocated when you add additional passes. We've already been doing this in nitrogen for years. When you shift nitrogen from anhydrous to weed and feed to sidedress to the planter, you still apply the total pounds for the year. You just move when you put that nutrient on. Okay, so our summary of optimized phosphorus, and a big reason why those total program plots create the results they do is that FurrowJet 8 to 10 gallon per acre continuous stream application seems to be the best result. So nitrogen, on the other hand, is a little bit different animal than phosphorus. And again, understanding the nutrient helps understand why we get the benefits we do. Nitrogen is a very volatile nutrient, where phosphorus is very stable and immobile. Nitrogen also is a major nutrient for the microbes early in the season. When you see a picture like this with a little bit of yellowing corn, a lot of times it's the immobilization or tie-up of nitrogen that the corn is struggling to get enough, and that's from the microbes firing up at the beginning of the year and consuming the organic material in the soil. They're also feeding on nitrate that's available, and they're competing with the corn crop for those nitrates, and every year the corn crop is going to lose and the microbes are going to win. So to manage that properly, you have to make sure that there's enough fertilizer nitrogen within reach of that small corn plant's root system at the beginning of the season, and you overcome one of the major flaws in a lot of nitrogen systems. And so we believe the best placement for that is about 3 inches to the side of the row. We like to incorporate nitrogen in the soil so we protect from volatility, and then we also are maximizing the crown root uptake. The first major roots that grow from the plant, they're going to grow right through that nitrogen band as it expands and grows a little in the soil. So I want to invite up next Jeremy Hodel is one of our project lead engineers, and he's been working on our product Conceal for the last few years, and he's going to talk about the process of designing that and working with that. And then when he's done, I'm going to come back up and show you some of our nitrogen trial data.
Thank you, Corey. Well, I'd like to share with you the story of Conceal. When we first set out to develop a nitrogen application product on the planter, we didn't really know what we wanted it to look like. But what we did know was what we wanted it to accomplish. So it was sort of like we started with a compass as opposed to a trail map. And our compass consisted of 2 guiding principles. Rule number 1 was get placement right. Knowing everything Corey's already explained and our research has shown about the importance of fertilizer placement, we wanted to get it right like none other. Rule number 2 was something my mom used to always tell me, which is the main thing is to keep the main thing the main thing. I guess technically she got that from Stephen Covey. I don't know, I haven't read that book. But we've all seen what happens when someone forgets this principle, right? Take this guy, for example. Looks like he's having fun. But how well do you think that mower cuts grass? It's the same with your planter. But don't get me wrong. Hear me on this. We believe applying nitrogen on the planter is a great idea. In fact, essential to a robust nutrient program. But not if it comes at the expense of your number 1 priority when you're planting. What's that? Putting seed in the ground. Uniform spacing and emergence. So our goal was to devise a system that got fertilizer placement right, but not at the expense of seed placement. But there's a lot of 2x2 attachments out there already. So why did we think at Precision Planting we needed to bring something new to the market? Well, we tried many of these options, and each of them has merit in the right condition. We also tried a lot of our own ideas. Justin Kaufman mentioned Derek Souter, and one of his legacies in the R&D department is the saying, "He who tries the most things wins." So we certainly did that. We tried a lot of things. But after talking to a lot of customers, testing many of the products that are available on the market, and even many of our own ideas, we had the benefit of learning, not only from our own mistakes, but also from some of the mistakes of others. And so we in essence learned what not to do. So we put together a list of things that we wanted to avoid. Coulters. They're really good at bringing up sticky dirt. Can you see all the dirt that's on the closing wheels on the system to the left? That's because there's a set of fertilizer coulters right in front of that closing system. And that would be true also if the coulters were farther out in front. Speed certainly doesn't make that situation any better either. Bearings and fertilizer don't mix well, especially bearings made of steel. If you think squirting or dribbling fertilizer into a trench is a good idea, you've obviously never been inside a men's restroom at a truck stop. How often have you seen a planter with closing wheels or other components that look like this, right? Not only are you going to make a mess of your planter, but what does that say about where that fertilizer product is going? It's a disaster for fertilizer placement too. We all know how difficult it can be to get closing wheels aligned properly as it is, so we didn't want to make that harder by extending the closing system. In this picture up here, we were seeking to demonstrate the effects of an extended closing system as you're planting around a curve. And so we actually applied water to mark where the furrow is on these two rows here in the middle. And as you can see on the row to the left with the extended closing system, those wheels are so far out of alignment that they're actually both on the left side of the trench. Obviously, that's not a good situation for closing. We also know that transport width and storage width can be an issue as it is, so we didn't want to make the row unit any longer than it was. And anything that's rigidly attached to your row unit, especially if it's offset in front of or behind the opener disc, is going to be potentially really hazardous for your row unit ride, your downforce consistency, and even potentially your seating depth consistency. So on the other hand, we came up with a few things that we really liked. If you want to get fertilizer placement right, it's hard to beat a knife. Knives are kind of like a speed tube for a fertilizer system. So in the same way that a speed tube doesn't let go of the seed until it's all the way in the ground, knives won't let go of the fertilizer until it's also in the ground. Knives are great too from a simplicity, there's no moving parts, and also from a packaging standpoint. Dual band. If you want to maximize your root accessibility to the plant, that's a great way to do it, putting fertilizer on both sides. And for heaven's sake, keep it simple. Planters are plenty complicated as it is, so we didn't want to make a fertilizer system any more complicated than it had to be. Well, with those ideas in mind, here's what we came up with. We stuck a knife right in front of the gauge wheel. But it didn't take us too long to figure out that we had an almost fatal flaw. It would have been a great idea if our goal was to just push residue in front of the row unit. Basically, we invented a rake instead of a fertilizer attachment. But we weren't ready to give up on the idea just yet. There was still a lot to like about it. So we went to the whiteboard and started brainstorming. So up here you can see the main problem we identified, which is residue snagging. But what I love about this picture is that it goes to show at Precision Planting there's no such thing as a crazy idea. If you look at the ideas list here on the left-hand lower corner, my personal favorite is this reciprocating knife action one. Unfortunately, we didn't get around to prototyping that one, but would have been fun. The one that gained the most traction, though, was this new gauge wheel profile. And as we tested and experimented with different things, we started to realize that the closer we got to the gauge wheel, the better off we were in terms of residue handling. So we just needed to get a little bit closer. So what's the next logical step? I'll get the Sawzall out. Two guys in the picture here to the left, Corey and Doug. They may look like hillbillies, but no, they're actually real engineers. And so this is what we do. We cut the gauge wheel open, and sure enough, that was a magical combination. We had all the benefits of a knife, the simplicity, the superior delivery, and the sleek packaging without the main issue of residue handling. The cool thing is that the very solution that solved our residue handling issue also put the knives in the absolute best position possible for consistent fertilizer placement. So whether you're planting on straightaways or around curves, having the knife directly beneath the gauge wheel ensures that the lateral position of that band is always going to be exactly 3 inches to the side of the furrow. So that ensures that we can apply up to 30 gallons per acre per knife without any risk to seed burn or early root burn as well. Likewise, having the knife directly beneath the gauge wheel ensures that our vertical depth of that band is always going to be beneath the surface, even if the seed bed isn't perfectly smooth. Of course, this is only the beginning. So in 2017, that was our first spring, we learned a ton. We made a lot of changes. And so in 2018, we came back around and did a beta season. This time, we covered territories all across the United States. We went from Georgia all the way up to North Dakota, and our goal was to make sure that Conceal was going to be robust in any condition that it experienced. And so that brings us to where we're at today. And as I overlay, as I show you the alpha side view, this is where we were a couple of years ago, and then overlay the production design. One of the things you'll notice is that as we've evolved this design, that knife has come farther back into the gauge wheel. And this is for the reason of improving the flow, not only of residue, but also soil. We've seen that made a big difference. It's for the same reason that we increased our ground clearance and streamlined the design. Well, running a knife inside a groove and a gauge wheel, that raises an important question about downforce consistency, right? If you think back to the number 2 principle, keeping the main thing, are we violating that principle with this design? I'd like to point out a couple of things about it. First thing you'll notice is that the knife and the gauge wheel are independent of one another. So I can move the gauge wheel without moving the knife and vice versa. The other thing to note is that we've incorporated a spring mechanism in this knife system. And what that does is it allows the knife to break away if it encounters a rock or any other sort of obstruction without bringing the whole row unit up with it. Also keep in mind the position of the knife. Since it's directly beneath the gauge wheels, that ensures that our ground that the knife experiences is always exactly the same as what the opener disc experiences. I'd also like to show you an example. This one comes from a side-by-side set up with one of the beta growers last spring. And as you can see on this map, we've got the left half of the planter shown in orange was a Conceal side. And then on the right side of the planter is a rigid coulter. So both are applying fertilizer with 2 different attachments, but split half and half. Blue is the rigid coulter, Conceal is orange. If we look at the downforce map, does anything jump out at you? How about all those blue blocks that represent a loss of ground contact? Do you notice how they tend to line up with the blue stripe coming from the rigid coulter? So what might be going on here? Well, if we pull up the applied force map, we can learn something else. As we see here, on the side, particularly the rigid coulter side, we had this system maxed out. It was applying greater than 600 pounds of force, and yet there still wasn't enough to get both the seed disc and the fertilizer coulters in the ground all at the same time. We're just running out of downforce. Whereas on the Conceal side, there was still enough to go around and to get both products in the ground. This is just a bar chart of the same field map, or the field data in a different format here. And just looking at the numbers, you can see how the Conceal side had a much less impact to downforce compared to the rigid coulter side. Obviously, we're putting something else in the ground, and it will take some force. But relatively speaking, it's an easier system for the planter to handle. I'd like to show you a few examples of Conceal running. This one here, this was just from a couple of months ago. Back in the fall, we were planting a cover crop into freshly harvested corn residue. No row cleaners on this row unit, so pretty harsh, high residue environment. This video was taken from last spring. One of the beta growers who worked with us out in Virginia was planting corn into a cover crop. Again, no row cleaners, pretty tricky environment. Here's one from New York from the beta as well. And what's probably hard to tell because the camera's a little bit blurry, the guy taking the video was probably about ready to get bucked off because the ride was so rough. But the knife is actually moving up and over those rocks as it encounters them. And then finally, this video was just taken a couple of weeks ago down in Texas. We were doing some last-minute testing with some of the production design components, and this is a very mellow seed bed environment in that situation. Well, I'd like to leave you with some thoughts from one of the customers who had the opportunity to test Conceal last spring. This is Cindy Pitzner, and she's from up in Wisconsin, so she'll share her experience with us. And then after she's finished, Corey's going to come back up and finish explaining some of our own trials and field research with Conceal.
When we were looking at doing the Conceal beta test, we were looking for a better way to place our fertilizer. I've tried a couple different things. I didn't like the functionality or the practicality of them, and I was looking for something different. And this Conceal product was very interesting. So one of the concerns we had back when we had the row-mounted fertilizer was the placement of the fertilizer in relation to where the unit was, because it was so far out in front. So when we went to the row-mounted unit, we thought, oh, this is going to ride with the unit better, and it's going to give us better placement of fertilizer. And it, I think, maybe did, but it does affect the way the row unit rides. One of the things I like about Conceal is it's right inside that row unit. When we're running the Conceal side by side with an in-between unit, a few of the observations I had is that the Conceal rode with the row unit much better. The in-between almost pushed like a lever, and I think it affected the down pressure, and you could see that on Delta Force actually, because the down pressure was different on the half of the planter that had the in-between versus the half of the planter that had the Conceal. So some farmers that had come by and saw this product on the planter, and they thought, oh, that's going to plug up and you're going to be dragging debris and so forth. And I never had an issue with debris dragging on the Conceal product at all. So it was kind of fun proving them wrong. In fact, I went into green clover, I went into standing high fodder dead clover, I went into rye ground that had been harvested, and I never had issues in any of those circumstances with any kind of debris. If we were running in a field with rocks, or running in a field with no-till, or in a field where that mud hole's hanging out there and you're going to catch it with the last 2 rows of your planter, you didn't have to worry about it. In the combine, I would notice in a side-by-side a couple bushel difference is kind of a standard thing. The co-op backed that up by saying, when they looked at stuff a little closer, about a 5 bushel difference between the Conceal side and the in-between. So the question is, will I put Conceal on the whole planter? And the answer is yes. We're going to put Conceal on the whole planter.
Okay. So we've of course been testing nitrogen options in the field as well, and learning about the bushel advantages and the profitability of shifting the nitrogen into different types of applications. We had a new trial. This is the first time we've shown this year, and it's working with the University of Illinois and using a stable isotope of nitrogen, which is the 15N on the left. And what a stable isotope is, it's a manufactured molecule that in environment acts the exact same as the natural molecule in the environment, so it's traceable, it's trackable, and it can be measured. So natural in an environment is 14N, and so 15N is 1 mole heavier, molecular weight, 1 mole heavier than the natural nitrogen. And so when you incorporate this into your fertilizer, you have a known amount that you can track as far as where did it end up, soil, how much is in the plant, how much went into the tile lines. Is a standard type of study that environmental scientists do as well. 15N, it's a little bit expensive. If we put 200 pounds per acre of 15N on a field, it would be about a $16,000 an acre nitrogen bill. So I've got a pretty good budget here at R&D, but it's not padded that much. So we've had to do this in very small scale plots, and we worked with Cropsmith out of Farmer City, and we had 3 different field sites and a lot of different replications, but each rep is just 10 foot by 10 foot, and we had to hand apply all of the fertilizer. And so we simulated broadcasting of 80 pounds of nitrogen versus the simulation of single and dual band of nitrogen incorporated in the soil right next to the row to be similar to what Conceal can do on a planter. The remaining 120 pounds of N to complete the 200-pound program was not traced with the 15N product, and it was just coulter side dressed across all treatments. So the variable that we're measuring is 80 units of N broadcast versus banded with the planter. And we had to harvest then all the plants by hand. We harvested the center 2 rows out of 4 rows in these blocks, and they had to be ground and then dried to process the samples. And we're processing that entire plant to learn about the total pounds of N that got into the plant from those 80-pound applications. And Dr. Mulvaney and his grad student Kelsey at the U of I, they run the lab side of things, and they've got this huge machine called a mass spectrometer. Basically, a mass spectrometer, you put the samples in one side, and it processes in about 10 different ways, and what comes out the other end is a computer-generated report of the amount of nitrogen that was in that plant sample. And so we're able to learn what the efficiency of uptake is. And so the value we're looking at is fertilizer nitrogen uptake efficiency of the different application programs. And so first off, the broadcast, only 27% of that nitrogen got into the plant. So where does the rest of it go? When we broadcast nitrogen onto the soil, the microbes consume it, it ends up in the organic matter, maybe some leached, maybe some volatilized in the atmosphere. We don't know exactly where it went, but we do know for a fact that only 27% of that got in the plant. When we band a single band next to the row, 43% of that nitrogen gets into the plant. And then the dual band, we're up to a 51% nitrogen use efficiency value. And so it was interesting. I didn't know that it was going to be this much different. But going from broadcasting that 80 pounds to dual banding that 80 pounds, it doubled the uptake efficiency, the difference between 27 and 51% of getting into the plant. So you can see how there's big opportunities to get a bigger return out of different ways of applying and managing your fertilizer programs, especially nitrogen. So we also have plots where we're looking at total program plots on a large scale. Jason Webster's in charge of these nitrogen trials, and we're 2 years in on these. We're going to continue to repeat them. This is using all liquid 32% nitrogen, and we're comparing what's the best value of broadcasting, planter banding, and side dressing. And we're putting 225 pounds in on total on every treatment, but we're shifting around where and when we apply that in across those 3 passes. So first of all, this chart represents each pair of bars that's a different color is a different nitrogen program, shifted around a little bit different. The bar on the right that I circled the top of is the Conceal side. So that's where we have planter banded in. The bars on the left of each color is the broadcast version of that same program. And so Conceal, or that planter banded in, is creating about a 6 bushel advantage over our 2 years in these programs. Looking at all the programs together and comparing them as far as the ROI of the 225 pounds of nitrogen, we're comparing it to the dotted line in the center there on the chart, that yellow bar. That's 50% weed and feed, 50% side dressed with a coulter at V6. And so you see the difference in profitability of shifting the nitrogen to different places. So on the right-hand side of this chart, it's a list of all the programs, and they're in order from top to bottom as far as best to worst. And what you notice is when at the top of the list, it's Conceal, 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 Conceal in those programs. All the programs that had some portion of the total nitrogen applied with the planter are doing the best. And there's $60 an acre added profit all the way to the left, the top bar, where we were 25% weed and feed, 25% planter, and 50% side dress as compared to the 50-50 program of weed and feed and side dress. And so the way that we apply and when we apply makes a big difference in efficiency of the same pounds of fertilizer. This is summarizing the 2 years of data from that plot, looking at the single N applications. This means 100% of it went on at either weed and feed or planter timing versus dual application versus triple application. And you can see there's a big difference there. There's $100 difference in profitability of the same pounds of N applied in these 3 different timings. So we can absolutely get more efficient with fertilizer and do things differently. To sum up this session, when it comes to the phosphorus, feeding that early plant, FurrowJet at about an 8 to 10 gallon per acre rate has been generating about $30 additional profit for us in our plots. And then banding some amount of your fertilizer with the planter is generating roughly $40 an acre in increased profit from multiple years, multiple plots. And so it comes back to this. My belief in the beginning that I was stating is that if we implement technology and better processes on our farms, I believe that we can further tighten up our investment in fertilizer and still get more yield and better profits from our nutrient program. So thank you for your time today. Hopefully you'll take something home that'll maybe help you on your farm, or at least stimulate some thought on some next steps. Appreciate you coming, and thank you.